Welcome to Electron Line. For the first time in history, we've been able to measure gravity waves. Gravity waves were predicted by Einstein over 100 years ago, and it was Einstein who proved that light was actually affected by gravity, which was really strange and almost nobody believed him at first, because in order for gravity to have an effect on something, the object has to have mass, and light does not have mass. But he was right. He showed that when light passes a very large object like a star, light actually changes direction or bends according to the bending of space, which proved that space is indeed bent because of the presence of mass. Now what happens when you take that mass and you start shaking it back and forth? Well, that causes the warping of space around the object to shake back and forth as well, which causes waves then to emanate from that object, now known as gravity waves. An object such as the Earth is in the path of those gravity waves. The Earth will then feel the effect of those waves and will bop up and down, get squeezed and pushed and pulled because of the effect of those gravity waves. It's not unlike what we see when we have electromagnetic waves. When we have a charged object and we move it back and forth like this, electromagnetic radiation will emanate, and then an object like a radio or a cell phone can pick those up. If you have a boat on the lake and the lake is perfectly still, but then you cause waves to exist on one side of the lake, as those waves then move across the lake and reach the boat will then bob up and down. So it's just like that when objects are affected by gravity waves emanated from an object that moves back and forth, causing the warping of space to move back and forth. To give you an example of how that will work is, let's say you take the sun and you start shaking the sun back and forth. Of course, that would be quite an event, but if you could do that, shake the sun back and forth 1,000 kilometers back and forth 50 times per second, which gives you a period of oscillation of 20 milliseconds, you would create gravity waves, and then when those gravity waves would reach the Earth, they would exert a certain amount of force on the Earth. Now we've calculated the force here, and then calculated the force per kilogram, which means that if a detector was hanging there on the Earth, and those gravity waves would pass, it would cause an oscillation in that detector of 1.10 to the minus 12 meters in amplitude. That's a very tiny distance, of course. That's 1/1,000,000,000th of a meter, and so that would be very difficult to pick up. In other words, that amplitude would be 100 millionth the thickness of a piece of paper. Imagine trying to measure an oscillation whose amplitude is only 100 millionth the thickness of a piece of paper. Now let's fast forward to the event that we just saw. 1.3 billion years ago, very far away at a distance of 1.3 billion light years, two black holes collided. We actually saw the aftermath of that collision. Now one of the black holes had a mass of 36 times the mass of the Sun, the other one had the mass of 29 times the mass of the Sun. When they approached one another, they got caught in the gravitational pull. They started circling one another. When we picked up the signal, they were rotating about one another at 30 times per second. 20 milliseconds later, they had accelerated to a spin rate of 250 times per second, and then the signal disappeared. It caused gravity waves of a wavelength of 10,000 kilometers when we first saw the signal, and then they shrunk down to an amplitude of 1,200 kilometers before they disappeared. Our very sensitive detector, which we have one in the state of Washington and one in the state of Louisiana, were able to pick up that signal. We had an object hanging there, we beamed laser beams to it. There's an interferometer that we use to try to measure the very slight motion of that. And the reason why we know that we actually saw the waves is because both detectors saw them at the same time, 7 milliseconds apart, which is the time that it took for the gravity waves to reach the first detector, and then 7 milliseconds later to reach the second detector. The oscillations of the detector were only 1 times 10 to the minus 18 meter in amplitude. Imagine that, much smaller, 1,000,000 times smaller than the oscillations we would get if we were shaking the sun back and forth. That oscillation amplitude is 100 millionth the diameter of an atom, or 1/1000th the diameter of the nucleus of an atom. And yet we're able to detect that. We're able to measure that minute amount of movement, and we detected it at both detectors at the same time. Imagine that. For the first time in history, we're able to prove that gravity waves exist, and we actually measure them. And that's how we do it.